Dual nature of radiation and matter. Maxwell equations of electromagnetism and Hertz experiments on generation and detection of electromagnetic waves in 1887 strongly established the wave nature of light. Towards the same period, at the end of 19th century, experimental investigations on conduction of electric discharge through gases at low pressures in a discharge tube led to many historic discoveries. The discovery of X-rays by Röntgen in 1895 and of electron by J.J. Thomson in 1897 were important milestones in the understanding of atomic structure. So it was found that at sufficiently low pressure of about 0.001 millimeter of mercury column, a discharge took place between the two electrodes on applying the electric field to the gas in the discharge tube. A fluorescent glow appeared on the glass opposite to the cathode. The color of glow of the glass depends on the type of the glass, it being yellowish green for soda glass. The cause of this fluorescence was attributed to the radiation which it appeared to be coming from the cathode. These cathode rays were discovered in 1870 by William Crookes, who later in 1879 suggested that these rays consist of streams of fast-moving negatively charged particles. The British physicist J.J. Thomson from 1856 to 1940 confirmed this hypothesis by applying mutually perpendicular electric and magnetic fields across the discharge tube. J.J. Thomson was the first to determine experimentally the speed and the specific charge to mass ratio of the cathode ray particles. They were found to travel with speeds ranging from about 0.1 to 0.2 times the speed of light, 3 into 10⁸ meter per second. The presently accepted value of E by m is 1.676 into 10⁻11 coulomb per kg. Further, the value of E by m was found to be independent of the nature of the material metal used as the cathode emitter and or the gas introduced in the discharge tube. The observation suggested the universality of the cathode ray particles. Around the same time in 1887, it was found that certain metals, when irradiated by ultraviolet light, emitted negatively charged particles having small speed. Also, certain metals, when heated to a high temperature, were found to emit negatively charged particles. The value of E by m of these particles was found to be same as that for cathode ray particles. So these observations thus established that all these particles, although produced under different conditions, were identical in nature. So J.J. Thomson in 1897 named these particles as electrons and suggested that they were fundamental universal constants of matter. For his epoch-making discovery of electron through his theoretical and experimental investigation on conduction of electricity by gases, he was awarded the Nobel Prize in Physics in 1906. So in 1930, the American physicist R.A. Millikan, 1868 to 1950, performed the pioneering oil drop experiment for the precise measurement of the charge on an electron. He found that charge on an oil drop was almost an integral multiple of an elementary charge, 1.602 in 10⁻⁻19 coulomb. Millikan's experiment established that electric charge is quantized. From the values of charge E and the specific charge E by m, the mass m of the electron could be determined. Next is the electron emission. We know that metals have free electron negatively charged particles that are responsible for their conductivity. However, free electrons cannot normally escape out of the metal surface. So if an electron attempts to come out of the metal surface requires a positive charge and pulls the electron back to the metal. The free electron is thus held inside the metal surface by the attractive forces of the ions. Consequently, the electron can come out of the metal surface only if it has got sufficient energy to overcome the attractive pull. A certain minimum amount of energy is required to be given to an electron to pull it off from the surface of the metal. This minimum energy required by an electron to escape from the metal surface is called the work function of the metal. So it is generally denoted by Y0 and made in electron volt. 1 electron volt is the energy gained by an electron when it has been accelerated by a potential difference of 1 volt, so that 1 electron volt is 1.602 × 10⁻⁹ coulomb. So this unit of energy is commonly used in atomic and nuclear physics. The work function phi0 depends on the properties of the metals and the nature of its surface. The minimum energy required for the electron emission from the metal surface can be supplied to the free electrons by any of the following physical processes. Thermionic emission. By suitably heating, sufficient thermal energy can be imparted to the free electron to enable them to come out of the metal. Field emission. By applying a very strong electric field of the order of 10⁸ volt per meter to a metal, electrons can be pulled out of the metal as in a spark plug. Photoelectric emission. When a light of suitable frequency illuminates a metal surface, electrons are emitted from the metal surface. These photolight generated electrons are called photoelectrons.